So hey everyone, my name is Vahe, and I'm gonna present my capstone project, which is a laser engraving CNC machine. And I have only one supervisor, and his name is Sarkis Zeytunyan, and my advisor is Armana Soterian. So I'm gonna briefly introduce what is a CNC machine. I'm sure everyone knows, but in case. So a CNC stands for computer numerical control, and it's a machine that uses code, which is also called G code, to automate the process of cutting, engraving, maybe milling or even drilling. So in this project, I am going to concentrate on the engraving type of machine. And my motivation for this project comes from my background, which is multidisciplinary, and it is mechanical, electrical, software, and control engineering. So this project kind of combines all of these domains together. And the next one is educational. I want to donate this project to the lab, and which will enable the future engineers learn and practice, and kind of bridge the gap between theory and practice. So let's talk about the development stages, which are three: the mechanical design, the electrical design, and the software integration. I'm gonna mostly concentrate on the mechanical design for now. And so there, in the beginning, there was this vision how the machine would look like. Based on that, I had to create some technical drawings and then check the manufacturability. If the drawing was kind of good and easy, but the manufacturability wasn't possible to do, I had to go back, update the technical drawing, go back to the very beginning, because if one part doesn't fit and they are kind of in a assembly, then changing this part results in changing the other ones. So this loop was continued until the manufacturability was guaranteed, and only then I was allowed to go on and create the 3D model. So this is the 3D model in SolidWorks. I have used top-down assembly technique. This is built from the scratch, and everything you see that is black, except the motors obviously, is 3D printed. I have used ABS because it was light, it was resistant to heat, and yes. And also this is the top view and the isometric view. As you can see, I have only two axes because this is a laser. Let's call this one X and this one Y. The laser head is adjustable and it can be heightened or lowered by the user. So in the very beginning, I wanted to use 2020 aluminum profiles, but after some discussions with my advisor, I decided to change it because it would add more rigidity if those were made by their 2040. So this, the probability, there was some chance that they could bend or vibrate and make some unnecessary movements. So it was kind of avoided. So this is the front view. As you can see, it is very similar to the real one. And I want to concentrate here and stop here and say that this part is very important because understanding this part will allow us understand this and this, because they are not the same but very similar to each other. So let's have a look at this part. So here I have the motor. It's an EMA 17 motor. On the shaft of the motor is GT20 pulley. It has 20 teeth, and on it is the GT20 belt. It is all connected by a coupler, which has two different diameters. One is inside, one is 5 millimeters, and the other one, which comes out of this side, is 8 millimeters. I did this because I didn't want to use this one 5 millimeters for this long range. So here is the assembly in which all the like rolling motion is converted. So here I have this part which was CNC machine. I could have bought it, I could have 3D printed it, but those two options were abandoned very quickly because the accuracy was very important, and it had to fit everything together, and everything had to sit on it very tightly. So these parts are 3D printed, and this one is a bearing inside, and it's a wheel. It was bought. So everything is, all of this is important, but the most important thing that every CNC machine has to have is the accuracy. So all of this accuracy was provided by this small part. It's a tiny part that is put right here, and it is here. So it kind of allows the user to regulate the rigidity of this part, so it doesn't rotate. So when let's have a look. Let's cut it from side and have a look inside. So I have cut this from this side, and I'm looking from this side. I'm seeing this. So here we have the fastener. As I said, it was CNC machine. Here is the eccentric nut, and on the other side is the eccentric spacer. I've done some research and found out that it was actually used, and it wasn't my idea. But in the very beginning, when I found out that there is this kind of thing, I was very happy because I made something very new. So, but they usually use from these two sides, but I avoided it, and this one was 3D printed. I did it because adjusting from both sides by hand is practically impossible. So that it doesn't matter how much effort you put, it can be kind of not linear, not horizontal. So whenever this is rotated by a wrench, this whole part goes up, and vice versa, it goes down. When it goes up, it kind of attaches all this part together, and it kind of doesn't vibrate. So after that, I went on and created this enclosure. I did this because the laser is harmful for the eye. Even though it has glasses, I still wanted to create some kind of enclosure because the user can use the glasses. But if someone comes into the lab, they might accidentally look at the laser beam. I used organic glass and red sheets. Obviously, I could have used a red organic glass, but I didn't do it because it would cost 5 times more. So, yeah. For the electrical part, I used CNC shield. It sits on the top of Arduino Uno. It is very simple and plugs directly onto Arduino Uno. It has 4 axes, X, Y, Z, and A. A is additional axis. I'm using only X and Y. So maybe for the future, it may be useful to have more axes. And also it has the places to plug in the jumpers, which allow to regulate the I forgot the name. Micro-stepping. In my case, it is 1/8. So I have used also the RV8825 for. Can I close this? Sure. So the RV8825 for my drivers. As I said before, I have used 1/8 microstepping because adding more microstepping would result more current, and the motors would heat up more frequently. Also, it has a built-in overcurrent protection, and it is very smooth. I have done some research and found some other drivers, but they are kind of too noisy and do not support microstepping above 1/16. So this is the laser. It's a diode laser, and the output power is 5.5 watts. It's a maximum power. It supports PWM. Usually, I have done some tests, and I have usually used 50% of the power. The wavelength is around 450 nanometers, which makes it a blue laser. And most important thing is its cooling. It has built-in fan, and it has also adjustable head. So all of this is controlled by a user who gives some input, which goes into the microcontroller, which in my case is Arduino Uno and the CNC Shield. Those two control the stepper motors, which consequently control the axis, and the laser module. Also, I have limit switches at the end of each axis. So this is the GRBL software. With when the user puts some image, it supports many types of images: PNG, SVG, or PENG. So whenever an input is given, it can be in the form of G-code or in the form of a picture. It allows the user to adjust the brightness and many other things. You can contrast it, you can rotate it, crop it, or other things, and it automatically converts it into G-code. It also, very important thing, is that it also supports some balanced laser power. So it can be either constant or balanced. When it is balanced, it goes this way and stops, and then when it has to engrave, only at that point it starts engraving. But if it is constant, it is always engraving. So what can it engrave on? I have tried it on wood and cardboard and paper. I am assuming that it can also very easily engrave on leather and fabric. I haven't tried it, but I can give a guarantee that it can do it. So this is the video of engraving it. It can do 6,000 millimeters per minute movement. The working area is 400 by 420, and the power consumption is 40 watt per hour. So these are the tests and results. I actually have it with me. You can have a look. It can be, let's talk about the applications also. So as I said before, I'm going to donate it to our lab, so it can enhance the practical knowledge of students. It can also be used in warehouses and have an industrial use. For example, if there are some parts and they need to be named, or maybe a QR code needs to be put on it, it can be used in that way. For small businesses and crafting, also I think it can be used for personalized gifts. I have actually done some before giving it. So this is all. Thank you.
Well done to make a working product.
Thank you.
Well done.
Yeah, I've also
contributed to the lab. So.
Yeah, I forgot to mention that I have also created a user manual for easier.
Maybe I'll just ask, what would of all the different challenges, what would you specify as your most difficult technical challenge, or it's something you're most proud of solving?
Yeah, I think the most important thing that for me was the mechanical design because there are lots of different types of CNC machines, and I wanted to make it kind of unique. So I took everything from every kind of CNC. Some of them have more rigidity, some of them have more electrical parts, some of them have better linear rotary to linear motion. So I think the challenge was if some parts were ordered or bought, they had some manufacturing defects, and I had to solve them. For example, this one, when I ordered these motors, the shaft was I think 25 millimeters in the drawing but it came as 23, and it was a huge problem. It's only 2 millimeters, but I had to cut it and kind of devise a way to put it so it can be coupled with this. Also, I wanted to avoid using 3 motors. You can see here I have added this. Because instead, I could have just added a motor from this side and avoid all this part. But I figured it out that I don't use this part at all because it moves this way, and it is kind of abundant space, and it also would make it more compact. And also I avoid it by doing it using another axis. So it may be used in the future by other students. Maybe they want to add something more, the third axis or whatever.
Great, thank you.
What is the cost of assembly?
Yeah, it's a good question because I have also concentrated a lot on the cost. It was very important for me. It is a little bit shy of $200, $197. In the marketplace, you can find this type of configuration with a cost of about $300.
So you have got business on your hands.
Yeah, I'm business person.
What was the precision of?
I think the microstepping is 1/8. It can be increased. The precision also will increase. But as I said before, I didn't do it because it would result in more current and more overheating. So it is possible by just adding a small fan in front of it, and the precision can be increased.
Good job.
Thank you.